Chris Panartis, and I'm here to tell you a few things about the Westside system in general and the Richmond transport facilities in particular, specifically about the hydraulic modeling effort that was conducted in this lab. This rough schematic here represents the Westside system. The facilities in black depict existing storage in the Westside transport box, the Westside pump station, and the ocean outfall, Southwest Ocean Outfall. This is the Oceanside Water Pollution Control Plant, which is currently under construction. It will be a 65 MDT wet weather facility. This is the Lake Berset Tunnel, which is currently under design, or the design has been completed and is going to go into construction fairly soon. The elements in red represent the Richmond transport facilities, which consist of a diversion overflow structure in the Richmond area, a 13-foot diameter tunnel that terminates near the Grey Highway, and a 4-foot diameter connection that we connect the Richmond Transport Tunnel to the Westside Transport Box at Fulton Street. The diversion overflow structure will intercept all the flows from the Richmond area, specifically the flows that are coming down from 17th Avenue, 22nd Avenue, and the 24th Avenue sewers. All these flows will be diverted into the Richmond Transport Tunnel, and through the 4-foot diameter connection, they will flow or discharge into the Westside Transport Box. The maximum discharge rate being around 108 CFS. That's a design requirement which relates to the reduction of the overflows. Now, before constructing any of these facilities, the overflows from the Richmond area used to be around 58 a year on the average. The requirement is to reduce these overflows to 8 a year. Now, this being a gravity system will depend on this small diameter pipe, small relative to the diameter of the tunnel, to dissipate the energy from a plus 50 feet to about plus 2 in order to restrict maximum outflow to the design rate of 108 CFS. Hydraulic model studies have been conducted to determine design parameters for a number of elements in the Richmond Transport facility. The first model concentrated on the geometry and the hydraulic aspects of the diversion overflow structure. The second model focused on the Richmond Transport itself, surges, air entrapment, dynamic pressure, and so on. And the third model concentrated on the connection to the Westside Transport and the testing of energy dissipating devices inside this 4-foot diameter tunnel. So today we're going to see tests for model number 2. That's the one which deals with the Richmond Transport, and model number 3, the one that was designed to test the 4-foot diameter connection to the Westside Transport Box and the energy dissipation devices therein. This is a close-up of the same schematic, and it shows the diversion of flow structure and 3 inflow pipes to the structure, the overflow discharge chamber, and the 2 pipes that would direct these overflows to Baker Beach for combined sewer overflow. Now, overflow will take place only when all the system in the Richmond Transport is full. There's the Richmond Transport Tunnel and the 4-foot diameter connection to the Westside Transport Box. All the dry water flows will enter the system through the 24th Avenue sewer and will discharge into the pipe at the upstream end, into the 13-foot diameter tunnel at the upstream end. So let's take a look at the model number 2, and watch what happens. Before we conduct a test with the model number 2, let's take a look at the upstream end of the tunnel and the diversion overflow structure. This is a diversion overflow structure which has been designed based on parameters derived from model number 1, which is shown in the background over there. Inflow into the structure, as we said earlier, takes place from the 3 points, the 17th Avenue sewer, 22nd Avenue sewer, and the 24th Avenue sewer. At the downstream end of the structure, that's the west side of the structure, is the beginning of the 13-foot diameter tunnel that leads to Gray Highway and eventually to the West Side Transport Box through a 4-foot diameter pipe. Inside the structure, there is a baffle and a weir. The baffle is to retain the floatables inside the system. The weir is set at 49.5 feet crest elevation to accommodate the overflows. On the north side, that's the downstream end of the structure, overflow-wise, there is a discharge channel and a discharge chamber which conveys the overflows to 2 existing pipes, a 5-foot diameter pipe and a 7-foot diameter pipe. Now these flows will discharge to Baker Beach in the form of combined sewer overflows. Now during the test, the total design inflow into the structure will have a peak flow rate of 1400 CFS. That's according to the CD 5-year design storm. 3 hydrographs will be input into the overflow structure via the 3 sewers shown here. The combined peak of the 3 hydrographs will be 1400 CFS. The hydrograph will have an early peak, and that's the combination which generates the highest hydraulic impact in terms of hydraulic behavior inside the tunnel, surges and dynamic pressure. Now why are we modeling the system here? To observe a number of things like air entrapment inside the tunnel and the need for air vents, if any, to let the air out. Watch for premature overflow at the upstream end over the weir. A premature overflow is an overflow which takes place before the total storage inside the tunnel is filled. It's a regulatory requirement. All available storage should be filled before we have an overflow into the receiving waters. Another thing that we're going to observe is the presence of hydraulic surges which will generate short duration dynamic pressures inside the tunnel. That's a very important design criterion. Now let's make a run and see what happens. Here's another view of the diversion overflow structure, 17th Avenue inflow, the upstream side, 22nd Avenue inflow, and the 24th Avenue inflow from left to right. The tunnel starts the left-hand side of the diversion overflow structure. It's a 13-foot diameter tunnel, approximately 10,000 feet long, flowing from right to left. The total storage volume in the tunnel, approximately 10 million gallons. There's flow in the tunnel tunnel loops around the warehouse and it terminates at the point where the black cap is. The small diameter white pipe is a connection from the downstream end of the tunnel to the west side transport box. A valve at the downstream end of the small pipe is used to regulate the outflow, which should not exceed 108 CFS approximately under maximum storage conditions. Here's the tunnel flowing full. With overflow taking place at the diversion overflow structure. There are the two pipes, the 5-foot diameter pipe below, the 7-foot diameter pipe above, directing the flow to Baker Beach outfall. This is a manometer which is used to observe hydraulic rate line elevation and also to show the extent of the surge, the dynamic pressure that's exerted on top of the hydrostatic pressure during maximum surge conditions. The green mark on the manometer represents hydrostatic conditions when the system is full, approximately 49.5 feet above sea level, San Francisco datum. A test with an early peak hydrograph. Here's the downstream end of the tunnel. Tunnel is filling. The formation of a surge which is moving upstream. There it is, moving upstream inside the tunnel and expelling the air which travels upstream on top of the flow. This is the manometer we're going to watch for surges. Now you have seen the dynamic pressure due to the surge rise up the manometer a couple of times. And now we're back to hydrostatic conditions. Since we are overflowing over the weir at approximately 52 feet, that's what the hydrostatic pressure is at this point. There's an air bubble. Small air entrapment will take place, but this is not serious enough to require vents along the tunnel. There it is. Here is the diversion overflow structure overflowing at approximately 1300 CFS. 100 or 108 CFS is being discharged into the west side transport via the small white pipe at the downstream end of the tunnel. There's the inflow from 17th Avenue, the inflow from the 22nd Avenue sewer, and the inflow from 24th Avenue, right there, and the upstream end of the tunnel. Now the overflow enters a discharge chamber, that's where the air vent is. Small air vent, and the flow from there enters two pipes, a 5-foot diameter pipe at the bottom and a 7-foot diameter pipe on the top. But at the beginning of the pipe, at the upstream end, there's a 9-foot diameter transition that was needed to minimize the entrance losses to the pipe and make the design of this structure viable. Let's go to the west side transport box. It's approximately 180 feet long prototype units. This is a downstream end. That's the west side transport box. That's the end of the pipe. At two locations along the pipe we have installed orifice plates to dissipate the energy. It's one of them. Label M1, that's a manometer where the hydraulic red line is measured. And further downstream, there's a similar orifice plate with a manometer on the upstream side labeled M2. At this point, there is a connection between the downstream and the upstream end of the orifice plate to experiment with releasing the air from the system. The standpipe represents something like a valve through which air can be let out or in. The maximum flow that would be passed through this pipe would be 108 CFS prototype units. We will observe what happens starting with a closed valve.